All right, let's start with kinetic energy, right? We're talking about work and energy, principle of work and energy. We explained that, what it is, and we're going to talk about both sides of this uh, equation, right? We're going to start with kinetic energy and look into kinetic energy and how does it, how come, or how is it different from what we had for particles, right? So for rigid body, uh, kinetic energy actually has two components or has two terms. It's not just 1 over 2 mv squared, right, like what we had for a particle. Since we have a rigid body, as I mentioned that a couple times before, the main difference between a particle and a rigid body is that the mass is distributed. So we have rotation. We care about rotation, the way the whole structure of the rigid body rotates or during the motion, whether it's rotation with a fixed axis or it's general planar motion. We take that rotation into account, and that's how the whole idea of mass moment of inertia came into play, right? Now, when we look at the kinetic energy of a rigid body, we also have to take into account that rotation. So the kinetic energy of a rigid body has two terms. We have a term for translational kinetic energy, as you want to call it, if you want to call it that way. And we have another term uh, because of the rotation that happens in a rigid body. So let me put it this way. So for a rigid body, for a rigid body, you can say fix the pen, kinetic energy, uh, let's say, has two terms. Uh, well, the first one is I'll call it the translational kinetic energy. Let's put this way: the translational kinetic energy, right? And let me write it this way: uh, due to the velocity, due to the velocity of the center of mass, right? So look at the center of mass as just a particle, and write down the translational kinetic energy equation 1 over 2 mv squared, the way we were doing it for a particle, right? Due to the center of mass, due to the, this way, due to the velocity of the center, apparently I didn't fix the pen, I thought I did, of the center, due to the velocity of the center of mass. And the second term would be the, let's call it rotational kinetic energy. The rotational kinetic energy. And that is caused by the rotation, like angular velocity. So let's put it this way: due to the angular velocity. Let me see if I have, there you go. Let's put here. So this is, let's say it's a rigid body, right? The center of mass represented by, let's see if I can put G here. Represented by G as center of, here is the center of mass. It has some linear velocity V, and there is some rotation. Can be around center of mass, can be around any other point. In this case, let's just say it's around the center of mass. So we have a general planar motion, right? the center of mass has some velocity, and we have angular velocity around the center of mass. Let me make this a little smaller so I can actually move it here. I need the space below this. Let's erase this, put it in the right place. There you go. This is G, center of gravity. So kinetic energy, the combination of these two terms would be 1 over 2 mv squared, right, velocity of the center of gravity, plus, fix that, 1 over 2, well, when it comes to rotation, we said, well, mass moment of inertia is pretty much the equivalent of mass in a rotational motion. So Ig, fix that, and angular velocity, omega squared. So that would be the equation to use for when we are dealing with general planar motion of a rigid body. How can we find the kinetic energy of that rigid body? Now, if we just have a rotation about the fixed axis, you can guess, right? We can actually combine these two, get rid of, there is no velocity. We can get rid of pretty much the first term because center of gravity or whatever particle or point on a rigid body we look at, it's not moving, right? It's just there is a rotation about a fixed axis. So as a result, the kinetic energy we're going to have only depends on the rotational motion. So we only have the second term. But in that case, well, it depends on which point we have the rotation about. In this case, we are just considering rotation about the center of gravity, but when we have a rotation, that rotation can happen around any specific point, right? That fixed axis can be in a specific point on a rigid body. So for that motion, we only have the second term, but the mass moment of inertia we care about is the mass moment of inertia about that center of rotation or axis of rotation. So let's put it this way: for rotation about this pen is making it difficult. For rotation about a fixed axis, what do we get? We can just write, well, kinetic energy only depends on the angular velocity, and we're going to look at the mass moment of inertia about that specific axis that the rotation is happening about it. I do have actually a picture, so let me just use it. So here is just for the motion about a fixed axis, right? If we have rotation about, let's say, point O right there, right? And we know the angular velocity, well, the kinetic energy of this rigid body would be just, can be easily calculated, right? As long as we know the mass moment of inertia about that point and the angular velocity with which the rigid body is rotating about that point, we can find what is the kinetic energy of this rigid body during this rotation about the fixed axis. Now, well, here is the kinetic energy part, right? We're talking about principle of work and energy. On the right side, we had T2 minus T1, right? The change in kinetic energy. That's how we calculate kinetic energy at any given moment for the motion of a rigid body. Now, looking at the work, the left side of the story. Now, pretty much similar to what we had for a particle, we deal with work in when it comes to rigid bodies. For any given point on a rigid body, we just follow the motion and we figure out the force and find out the internal or inner product of the force and dr. If you remember, when we were dealing with this type of and we're dealing with the work for a particle, we define that as the work done is pretty much is from point 1 to point 2 is equal to integral and let's say here we call it RP1, position of any specific point we are interested, the point that the force is applied. Right? So in this case, the force is applied to this red point on a rigid body. So the position of this point at the beginning of the motion and the position of the point that the force is applied at the end of the motion. And then we also care about the angle that force is creating, or that force vector is creating with the position vector at these two moments, at the beginning and at the end. So again, it's integral of the force inner product of dr. What is dr? dr is the change in the position vector, which shows the distance or the position of the point the force is applied to at the beginning and at the end of the motion. Let me write it down. So work done, let's put this on a rigid body by a force F as the point, let's put it, the point of, let me move this equation a little bit, just gonna move it here, maybe actually here, this is better, as the point of application accurate, the precise definition. The point of application of the force moves from position RP1 to position RP2, and that would be this. Now I can actually move it back. That would be this. Right? The integral of the inner product, let me see, of the force and the change in the position vector going from position 1 to position 2. Well, we care about the point that the force is applied. Now, this is very similar to what we were dealing when we were dealing with particles. In this case, the point that the force is applied, we look at that point as a particle. Now, there is another term or another situation that can happen, and that's when we have a couple applied to a rigid body or part of a rigid body. Right? Now we not only have forces, but also have couples or torques applied to our structure. So they can also do work. Right? So the equivalent of this, when we are dealing with rotational motion, well, couples are associated with rotational motions. They cause rotational motions. When we find the equivalent of this, or we deal with this expression in rotation, well, force will be replaced by couple. By couple, any kind of couple is applied to a structure, rigid body, and dr, which is the change, the position vector from point 1, well, change in position vector from point 1 to point 2. Now it's going to be d theta, right? Change in rotation, right? How much theta changes, and where does it go when the rigid body moves from point 1 to point 2. So let me write it down so it might makes more sense. Work done, let's say, on a rigid body by a couple M as the rigid body rotates this time from angular position. I'm going to put it here. Angular position. Can do better. From angular position theta 1 to angular position theta 2, almost there. In this case, we get the work done on the rigid body going from point 1 to point 2, well, equivalent of what we had for a force in rotation. So going from theta 1 to theta 2, m d theta. M d theta. And that'll give us the force, the work done on a rigid body because of the couple applied to it. Well, if there is no couple applied, obviously this is going to be 0. Just one thing, keep in mind, theta in this equation is always in radians. So theta is in radians. If you are given theta in degrees, definitely convert that to radians and then use this expression to find the work done by the couple.